For the longest time, the story of AI has felt like this simple race. Bigger, deeper, faster, more power, right? But what if I told you that underneath all that noise, something way more fundamental is changing? We're talking about rewriting the very DNA of how AI works.
And hey, don't just take my word for it. Researchers over at Google DeepMind, they're calling it a quiet revolution. That's a pretty big claim, right? They think we're on the cusp of a whole new golden age of discovery, all thanks to a totally new kind of AI.
So that begs the question, what is this revolution really? Is it just about having faster computers? Just throwing more data and more processing power at the same old problems? Or is something much deeper going on here? Something about how science itself works.
To really get our heads around that, we need to put on a different hat. We need to think like an economist, but for science. Because think about it. Every single scientific idea, every experiment, it all boils down to a trade-off, right? There's always a cost, and there's always a potential reward.
And there's this fantastic term for it from the philosophy of science. It's called pursuit worthiness. I love that word. It's really just a fancy way of saying, is the juice worth the squeeze? Is the potential discovery you might make actually worth all the time, the money, the sheer effort it's going to take to get there?
Okay, and this is where AI comes in and just flips the whole table. It's a total game changer for pursuit worthiness. It does two incredible things. One, it can actually increase the potential reward, what they call the epistemic gain, so bigger, more valuable answers. And two, it can slash the practical cost of actually doing the science. All of a sudden, ideas that were just, sci-fi, way too expensive, way too complex, they're now on the table. They're actually possible.
So to see how this actually works, how this economic shift plays out in the real world, let's zero in on one of the biggest, most crippling problems facing today's AI models. It's this weird kind of digital amnesia. It basically makes it impossible for them to truly learn over time.
And the analogy researchers use is, well, it's pretty striking. It comes straight out of neurology. They call it anterograde amnesia. You've probably seen this in movies. It's a condition where someone can remember their entire past, everything before an accident, but they can't form any new long-term memories. Every day is a blank slate.
And this is a perfect map for how a large language model works today. Its long-term memory, that's all its pre-training data, everything baked into its brain from the start. Its short-term memory, that's the context window, the conversation you're having with it right now. But here's the huge problem, the missing piece. It can't turn that short-term experience into long-term knowledge. It's missing what scientists call online consolidation. It experiences new things, but nothing ever sticks. It can't really learn from you.
So what if you could cure it? What if you could give AI a real, lasting memory? Well, that's exactly the goal of a radical new idea called nested learning. And it's not just a tweak, it's a complete rethink of how these models are built from the ground up.
So what is nested learning? Well, instead of thinking of a model as just this one giant flat stack of layers, it says we should think of it as a set of nested problems, almost like a company, right? You've got teams working on the day-to-day stuff moving really fast. Then you have managers working on quarterly goals a bit slower. And then you have the CEO and the board thinking about the 5-year plan, moving much more slowly. Nested learning builds an AI that works just like that. Different parts learning at different speeds all at the same time.
And this image here shows you the difference perfectly. Look at the left. That's traditional deep learning. It's basically a black box. Everything just kind of happens at once. But now look at the right. That's nested learning. It cracks open the black box. You can see this incredible multi-level structure. You're seeing the different parts, the different departments, all working and learning at their own pace. It's like finally being able to see all the individual gears turning inside a complex machine.
And what this all leads to, the really crucial part, is an AI that can learn and form memories in a way that is just so much closer to how our own brains work.
Think about your own brain for a second. It doesn't have one single clock speed, right? As you can see here, you have all these different brain waves, different frequencies, all firing at once. Some parts are processing things super fast, some much slower. And nested learning copies that exact principle. It builds parts of the AI that update incredibly quickly for what's happening right now. But at the same time, other parts are updating way more slowly, taking their time to really absorb information and turn it into permanent knowledge. It's that mix of speeds that's the secret sauce.
And this gives rise to something they're calling the continuum memory system, which is just so cool.
because it gets rid of that old binary idea of just short-term versus long-term memory. Instead, you get a whole spectrum, a continuum. You have these different processing blocks, each one ticking away at its own speed, handling memory for its own specific time scale, from seconds to minutes to hours and beyond.
So this isn't just theory. There's an actual architecture called HOPE that's built on these ideas, and you can see the difference clear as day. On the right, that's your standard transformer. Powerful, sure, but it's kind of flat. It's static. Now look at HOPE on the left. It's dynamic. It's multi-layered. You can literally see the different networks operating at different speeds. Fast ones on the inside for immediate stuff, slower ones on the outside for the long-term memories. It's just a fundamentally more sophisticated and, honestly, more brain-like design.
So does it actually work? Well, the proof is in the pudding. When you put HOPE up against other powerful models of the same size, like Transformer++ or RetNet, on common-sense reasoning tasks, it consistently comes out on top. So yeah, this more complex, more bio-inspired architecture isn't just for show. It actually delivers better results.
Okay, so we've been deep in the technical weeds. Let's pull back up. What does all this actually mean? Let's go all the way back to the beginning, back to that idea of pursuit worthiness, and connect the dots.
Here it is. This is the heart of the revolution. For decades, building an AI that learns at different speeds like a brain, it was a cool idea, a dream, but it was just too complicated, too expensive to be practical. It wasn't pursuit-worthy. What nested learning does is it gives us the blueprint. It provides the framework that finally makes these brain-like systems achievable. It radically lowers the cost of asking that huge question, what if an AI could actually learn the way we do?
And that's why they call it a quiet revolution. See, it's not about some flashy new model that tops a leaderboard for a week. It's much bigger than that. It's about AI changing the very rules of the game for science. It's changing the questions we can even dare to ask. These incredibly complex, dynamic, brain-like models, they're not just on a whiteboard anymore. They're becoming reality. This, right here, is what a new golden age of discovery actually looks like.
Which leaves us with one last, kind of mind-bending question to chew on. If we're building models that don't just learn, but can actually learn how to learn, are we just making better tools, or are we building our future colleagues?